have around 10 minutes of Q&A. And for Q&A, you have two options. On the Hoover, you will have this box to raise your question in the Q&A little box. And in here in the Zoom, you will have the raise hand function here at the bottom right corner of the Zoom. So either way, you can ask questions, and well, I will well, we will handle this Q&A. Yes. And so without further ado, let's welcome the first speaker. And I will give a brief introduction of this first speaker. Xingyu Chen received the bachelor degree in computer science from Harbin Engineering University in 2016. He is currently a PhD student with the Department of Computer Science and Technology at Nanjing University. His research interests focus on network security and RFID system. He's a student member of the IEEE. Okay, so let's welcome Xingyu. Hi, Xingyu. You can turn.
Okay.
Great.
Okay.
Great.
I will give my presentation. Can you see my screen?
Yes, we can. Yeah.
Okay. And hello, everyone. I'm Xingyu Chen, a PhD student from Nanjing University. In this talk, I will introduce an efficient method to do range detection in a commercial off-the-shelf RFID system. Here is the outline of this talk, including 4 parts: background, system design, evaluation, and conclusion. RFID plays an important role in IoT applications. A typical RFID system consists of 4 parts: the computer, the reader, the antenna, and the tag. Since a tag is cheap and battery-free, it is a good choice for many applications in our daily lives, including our ID card and the supply chain. In this work, we study how to do range detection in RFID systems. So what is range detection? It means to collect RFID tags with data between an upper and a lower boundary. It can be used in some practical applications. For example, in a supermarket, the staff may need to do the live query for checking whether there are expired products by collecting the sell-by data from tags. Another example is temperature detection. Consider a chilled food storage chamber where each food is affixed with a tag equipped with a small sensor. If the temperature data of a tag is higher than a threshold, an advanced warning should be activated to protect people and products. From the above 2 examples, we know that range detection is very important. Now, formally, we give the definition of range detection problem. Given a tag set T, which has n tags, we need to find a subset T prime of T that consists of m target tags. The target tag means the tag with data in a certain range. For example, there are 18 tags, and the reader tags are the target. In traditional way, we need to collect each tag exclusively, one at a time. We collect the first tag, the second, third, and the last. After collecting data from all tags, we know which tags are the target. This kind of collection is referred to as exclusive collection. This works, but is not efficient, especially in a large RFID system with a lot of tags. The low time efficient of exclusive collection is due to the fact that the reader has to communicate with each tag even though the tag is not the target. If we can silence most of these tags, a great deal of communication overhead can be avoided. I mean silence the blue non-target tags. Based on this idea, we propose the selective query. Selective query divides the collection into rounds. In each round, the reader deals with a group of tags that have the same data. This is very common in our daily lives. For example, in the supermarket, many products have the same sell-by date. If a group contains target tags, the reader will collect it one by one. Otherwise, the reader will silence this group and move to the next round. In this case, the reader can avoid collecting the first group and the fourth group, and thus it can save a lot of time. Now I introduce how to implement this process in practice. Generation 2 is the widely used RFID standard. It defines the physical and logical interfaces between readers and tags. In this work, we use two related functions in Generation 2 protocol to silence the tag that is not target. The first function is the select command, and the second function is the query command. And then I first introduce the select command. This command allows a reader to choose a subset of tags to reply. The select command has 6 fields. The first is target. It indicates which flag to be used. A tag has 4 inventory flags. These flags are used to do inventory control. In this example, target is equal to Wang, so the first inventory flag is used. The second field is action. It shows how can we set the inventory flag. The last 4 fields determine which tags are matching. If the string stored in the tag's memory is the same as the bit mask, then the tag is matched. In this example, the reader tags are matching due to the bit mask 1, 0. Their flags are set to B, while others are set to A. The second function is the query command. By using this command, we can let text with state A or B reply to the reader. Query command has 3 fields. The field CH means which inventory flag to be used. The field target determines which text will respond, where 0 means the state A and 1 means the state B. In this example, all text with flag B will reply to the reader. In this paper, we didn't use the SEL field, so I will not introduce it here. Then we introduce how to realize selective query with the above 2 functions. The reader first sets all text flags to A with a select command. In this select command, the target field is set to 2, so the inventory flag 2 will be used. The action field is set to 0, so the matching tags are set to A, while the non-matching tags are set to B. The bit mask is empty, so all tags are matching tags, and their inventory flags will be set to B, will be set to A. After that, the reader randomly collects an A tag through a query command. In this case, the reader is collecting data from the first tag. Since it is not the target tag, the reader silences all tags in its group by setting their flags to B. One select command is used to do this job. In this select command, the action field is 5. It means if tag matches the bit mask, its flag will be set to B. Otherwise, its flag will keep unchanged. We use the data of the first tag as the bit mask, so all tags in its group are matching, since they have exact the same data in their memory, and their flags will be set to B. After that, the reader starts a new round and queries the fourth tag. Since the fourth tag is a target, the reader will do nothing and collects the fifth tag.
Hello, Xingyu. Hello, Xingyu. Sorry for the interruption.
Okay.
I think there's a problem with your sound. Is it possible that you don't use your wireless headphone?
I don't. Okay, I can close my headphone. Okay.
Yeah, because there's some problem. There's a problem with the sound. I mean, from time to time.
Okay, can you hear me? No.
Yes, I think now it is. Maybe you can try to speak some more words.
Okay.
Yeah, now it is much better.
How? Okay. Okay.
Okay, sorry. You can continue.
So I continue my presentation. Since the first tag is a target, the reader will do nothing and collect the fifth tag, the sixth tag, and the seventh tag. The eighth tag is not a target. Its group will be silenced. After all tags have been set to B, the reader terminates the collection process. As we can see, through selective query, the four reader target tags are successfully collected. In this case, the selective query uses 6 readings to collect 4 target tags. 3 unnecessary readings of the non-target tags can be avoided. Although selective query is very efficient, it's still worth noting that a selective query still needs 2 redundant readings when silencing the tags in group 1 and group 4. If we can remove the 2 tags from the collection process, the time efficiency will be further improved. To achieve this goal, we propose a range query. The basic idea of range query is setting the target tags to A while other tags to B. After that, the reader can solely collect these reader target tags with a query A command. Instead of searching all possible values in the target range, range query uses left several bits as a bit mask to choose multiple values together. For example, suppose we want to collect a tag with data below 73. The bit vector of the upper boundary is given as follows. As we can see, we first find the first one, and then we take the left 1 bit before the first one together with a 0 as the bit mask to choose tags. As we can see, the tags ranging from 0 to 63 are set to A. After that, we find the second one, and then we take the left 4 bits before the second one together with a 0 as a bit mask to choose tags with data between 64 and 70 and 71. Finally, we take the left 7 bits as a bit mask to choose 72 and 73. As we can see, all target tags have been included. And we can collect them with a query A command. If the range also has a lower boundary, for example, 32 in this case, by using the same method I introduced before, we can first set tags with data below 73 to A, and then set tags with data below 32 to B, and then all target tags are set to A successfully, and we can collect them through a query command. We set up a prototype of range detection. This is the experimental settings. As shown in Figure 1, 4 models of RFID readers are used to better mimic a real RFID system and study the performance of our protocol in practice. We set up the experiments in a library, where up to 1,000 commanded tags are used, which is shown in the right figure. We'll also test the compatibility of our method and range query functions properly on all reader models and all tag models. Here, we test how many select commands does the range query need to collect the target tags. In the experiment, we vary the length of data from 1 bit to 16 bits. As we can see, the number of select commands increases linearly with the length of data. This is because more ones will occur in the bit vector I introduced before. The maximum number of the selects is 16. This small number will indicate that range query is time efficient. In this experiment, we evaluate the time efficiency. Since there is no existing work that studies range detection, we compare the execution time of range query with exclusive collection and the selective query. The 3 factors are taken into account, including the number of tags, the ratio of target tags to all tags, and the length of the data. Clearly, range query is more time efficient than the other 2 methods. For example, in the case with 1,000 tags, the execution time is reduced from 4.8 seconds to 0.2 seconds. The performance gain is 24 times. I think this is a great performance boost. Now I conclude this work. In this paper, we propose an efficient solution for range detection. In a large RFID system, our protocol exploits 2 functions defined in Generation 2 protocol. It can improve the time efficiency of range detection by collecting tags with data in a target range instead of collecting all tags in the field of view. We implement a prototype of range query with 1,000 tags. The experiment results show that our method can improve the time efficiency by an order of magnitude. That's all. Thank you.
Okay, so thank you, Xingyu, for the presentation. So anyone who wants to ask a question can either input it in the Hoover or raise your hand, or you can maybe simply turn on your microphone and ask a question. Does anyone have a question? Does anyone has a question? Okay, maybe I will have a question first. So I have already inputted in the Hoover. So you said that you conduct the range detection. So I want to know whether this range should be continuous, or can we have discontinuous? For example, I want to pick up all the tags from 0 to 30. and from 40 to 60 to 40 to 60? Can we have discontinuous range?
No, our method can only collect tags in a continuous range. If you want to collect tags in discontinuous ranges, you should conduct each collection one by one. I think we will improve this. We will handle this problem in the future. Yeah.
Okay. Does anyone else have a question? Does anyone else have a question? Okay, I have another question maybe. So you say that you kind of rely on the function of the generation 2.
Generation 2. Yes.
Right. So how hard it is to kind of use that function or modify the I don't know, the packets or whatever in the packets of the RFID, like how hard it is. Is there any trade-off of your solution?
Oh, okay. I know that. To the best of my knowledge, most commercial RFID readers have already implemented this protocol. We test, for example, we test for mostly widely used RFID readers, commercial RFID, commodity RFID readers, and they all support this protocol. So I think our method can be is practical. It can be implemented in practice in most RFID system. Yeah.
Okay, so is there any like overhead or trade-off of your solution? Overhead, extra overhead, yes. Or yeah.
Yeah. Okay. Yes. Compared with the exclusive collection, we need to use the more select command to select the tags in the target range. So the select command will have some trade-off. In our experiment, we found each select command takes about 20 million seconds. This is quite a short time. And in this, as I introduced in our method, in this experiment, even in the worst case, the maximum number of selects is 16. So so this small number will not largely affect the time efficiency of our method, because the 16 select command only costs about 0.3 seconds.
Okay, I see. So anyone else? Anyone else who have a question for Xingyu? Sorry. Anyone else? Okay, I will check the Hoover. I guess there is no further questions. Okay, so thank you, Xingyu. Okay, thank you. So we will move on to our next speaker. Okay. Okay, you can just Xingyu, you can just turn off your camera and your microphone.
Okay.
Yeah. Okay, so we'll just wait a minute. Okay, so the second speaker is Jeongmin Kim. He's a PhD student at KAIST from the Department of Electrical Engineering. His research interests include mobile system, IoT, protocol analysis, and blockchain. And today he will give us a presentation of Lumos, improving smart home IoT visibility and interoperability through analyzing mobile apps. So,
yeah.
Hi, Jeongmin. I don't think this is the first page of the PPT. Oh, okay, sure.
Yeah.
Great.
Okay.
Okay.
Yeah. Hello, I'm Jeongmin from KAIST, advisor under Professor Dongsu. I'll be talking about a system called Lumos, which enhances smart home IoT visibility and interoperability by analyzing mobile apps. Smart home integrates diverse smart devices, including sensors, actuators, and home appliances. The market value is expected to reach about $150 million by 2024. To increase their market share, major players such as Google, Samsung, Amazon, and Apple are struggling. Because of this, there are many IoT devices and platforms. We call this situation IoT fragmentation. Is a significant barrier that ties interoperability and the wider adoption of IoT services. This figure shows three major IoT platforms and the number of devices they support. There are three observations. First, only devices on the same platform are interoperable. Second, if devices belong to a platform, they are not into that specific platform. We suspect that these limitations are implementation costs and business partnership. The last thing is that many IoT devices are still standalone, which means that does not belong to any of the three major platforms and cannot interact with any devices on these platforms. There are many attempts to overcome the problem. In the research area, many approaches propose general IoT architecture, but it requires to entirely change to current IoT infrastructure. In the other hand, there are industry projects based on the general interfaces to control various devices, such as IFTTT, OpenTTT, and home assistance. But such approach also require vendor support, such as opening REST APIs. Because of these limitations, they are not widely deployed. So our goal is interacting IoT devices without vendor participation and improving interoperability without architectural modifications. For our goal, the key insight is that mobile apps play a key role in communicating with IoT devices and platforms. They contain valuable information for interoperability. First is the ability to control and monitor IoT devices. In addition, GUI of the apps includes semantic information. For example, this button is to power on a plug. Therefore, our system extracts this information and then uses it for interoperation among IoT devices that are not interoperable. I will show you an interoperation that is achieved by our system. In this scenario, we assume that a user wants to power off a smart plug, Wemo inside, when streaming a Netflix movie through a streaming dongle, Chromecast. I will show you how to instill our key insight into our system. Our system called Lumos has two software components. Lumos app is a mobile app that provides two operating systems, teaching and configuration mode. By using teaching mode, a user can teach Lumos semantics of IoT operation that he desires. Moreover, the app records users' interactions. I will describe it in detail in system design. Other component is Lumos Gateway, that is a middle box. It is operated in a general PC or a gateway that can run on custom OS. If a user performs a specific IoT operation on an IoT app during teaching mode, the IoT app issues network messages to control IoT devices. Lumos Gateway learns the network messages. It then uses the learned information to monitor and issue status or control messages for interoperation. Now, the user configures an interoperation rule on Lumos app. For this, Lumos app provides configuration mode, which is programmable interfaces for automation. Interoperation rule supported by Lumos consists of condition and control. Condition is a trigger to the specific action of an IoT device. Therefore, in this example, condition is streaming a Netflix movie. Control is power off or flow. If Lumos gateway detects the condition, it issues a corresponding control message to power off or flow. Now I will show you a demo video how to use Lumos app. In this video, a user performs teaching Lumos and configuring a rule for previous interoperation example. To achieve our goal, there are 3 challenges. First is identifying a specific message because there are many unrelated traffic in background. Second is how to learn semantics for specific status or control messages. The last challenge is supporting interoperation without any changes to current IoT architecture. This is our framework overview. There are 4 main pages that address each challenge. As I mentioned earlier, there are many unrelated background network messages when our gateway learns control or status messages. So the objective of this module is to pair a UI component with regular expression signatures for control or status messages. To identify the exact control and status messages that the UI component generates, we start from an existing tool, Extractable. It performs a static taint analysis to extract network message signatures that an Android app generates or receives. It also provides a core graph for an application. We use the information to identify a corresponding UI component that generates the signature. I will skip this module because we just used the signature building module of Extractable. We extend Extractable to pair a UI component with network signatures. First, it analyzes core flow graph from request sending functions until finding event listener. After that, we identify an object that has the event listener. After that, through taint analysis for the object, we obtain resource ID for UI component. In this figure, the resource ID is 7F0D009C. We also find a plain text label in XML manifest based on the hex ID. In this case, the UI label is brightness underbar slider. Lumos sets the label as a default semantic tag for the network signature. Note that this default semantic tag might be modified by user in semantics learning page. Statically extracted message signatures do not provide runtime values, such as URIs, query strings, and headers. However, Lumos should be able to construct a network request for monitoring and controlling IoT devices. To address this, Lumos integrates a runtime packet learning module. This module takes network messages and outputs learning instances that consist of UI and signature pair with values that are determined at runtime. Lumos gateway detects and captures the network messages that match the network signatures. Packet learner in Lumos gateway obtains the values. Moreover, it filters some of the attribute values not change over time by automatically generating the same network messages. The automatic task is performed by using the recorded user's interactions from the teaching page. Filtering the attribute is important because even if a user operates same actions, network messages might different. This example is to power off a Wemo inside plug. As you can see, binary state is unchangeable, but request time is changeable. To exactly recognize an IoT operation, Lumos gateway should know this characteristic. As I mentioned earlier, Lumos extracts UI label and sets as a default semantic tag from program analysis page. However, default semantic tag might be insufficient. To address this, Lumos allows users to modify default semantic tag. There are two cases when default semantic tag is insufficient. First, some UI labels do not contain any semantic information. Case 2 is that a single button may even trigger a different action depending on the context. This figure shows one example of case 2. This app is Linux Air Cleaner app that allows users to power on a cleaner with wind force level. As you can see, depending on wind force level, network messages are changed. In this case, users should teach Lumos. Last page is to support interoperation without any changes to current architecture. In this step, a user configures an interoperation rule on Lumos app, then gateway operates the rule by monitoring and issuing network messages. Interoperation support has two modules, which are Interoperation Builder and Learner. Builder is run on Lumos app that allows users to build interoperation rules. Interoperation rule by Lumos consists of multiple conditions and control actions to enable complex interoperation. In particular, there are two types of conditions. First is passive condition that is detected by monitoring network traffic without Lumos gateway sending any traffic. Active condition involves our gateway asking for a device status directly by sending a learned network message. After the rule registration, Interoperation Learner first monitors network message to detect condition triggering. If conditions are satisfied, Interoperation Learner reconstructs a proper control message from learning instances and send it. For evaluation, we try to answer three key questions. First, we check whether Lumos enables interoperation across diverse IoT devices and platforms. Second, we also show the capability of Lumos in terms of emulating key functionalities of the IoT apps. Third, we evaluate the usability of Lumos app through a user study. We evaluate Lumos using 3 popular platforms, SmartThings, Wing, Insteon, and 15 IoT devices with 9 mobile apps. 5 devices of 15 are standalone, while the rest belongs to one of the 3 platforms. This table presents IoT application and devices with their types in our dataset. With this dataset, we analyzed the coverage of Lumos compared to the 3 popular IoT platforms. SmartThings and Wink support only 5 and 6 devices. In particular, Insteon cannot interoperate with any of the other 2 platforms. In contrast, Lumos has much wider coverage than existing platforms. It supports all of 15 devices in our dataset. We also show the capability of Lumos in terms of emulating key functionalities of the IoT apps. For this, we manually identify the functionalities that IoT apps support. From the manual analysis, 29 functionalities are supported by the apps. We then compare Lumos with OpenTTT. OpenTTT defines common IoT schemas consist of properties for similar devices. Therefore, the schemas of OpenTTT well reflects a general functionality of various IoT devices. Lumos supports all 18 status query features and all 11 control features. In contrast, only 10 are supported by OpenTTT. Moreover, 7 out of 15 devices do not have an OpenTTT schema, such as a DORAG and streaming dongle. Even the devices that are supported by OpenTTT do not expose all their features, such as Nest Protect. This is because either the schema only defines minimal features for each device type, or the vendor partially implements the translation from the common schema to its own features. The last question is about the usability of Lumos. For this evaluation, we conducted a user study in which we requested our participants to use Lumos. We recruited 24 participants from the local university community, and we grouped the participants according to IoT experience on a 3-point scale. For our user study, we programmed 5 interpretation missions to directly compare Lumos with platform-native apps that provide programmable interfaces for automation. We designed 3 missions to program an interoperation rule using the existing platforms as well as Lumos. In the table, the devices column stands for the count of used devices in each mission. In particular, the condition column means the relationships between conditions when a user configures that interoperation rule. For example, the SmartThings mission is that a user turns off SmartThings plug and Q bulb connected to SmartThings hub if SmartThings motion sensor does not detect any motion and door sensor is closed. Therefore, it consists of 2 conditions and 2 controls. To compare with the result of each participant, we measured the number of clicks and the time for completing each mission. To demonstrate that Lumos app has reasonable entry barriers, we compared platform-native apps and Lumos app for Insteon, SmartThings, and Wink missions. As a result, 23 out of 24 participants succeeded in all 4 missions. In general, using Lumos app for all missions except Insteon took more time and more number of clicks compared to existing platform-native apps. This is because unlike platform-native apps, Lumos has teaching pace, which takes most of the user time. When looking at the time and clicks for configuration alone, Lumos app is considerably faster. We note that teaching results are reusable. It means that if Lumos app has already finished running a specific IoT device's action, users just need to decide whether it is a condition or control in configuration phase. This graph shows the average time required to complete each mission by 2 groups. First group is the participants who carried out the mission as the first mission. Other is the participants who carried out the mission as the last mission. So therefore, first I denotes the average time of those who started with the mission I, and last I is the opposite. As you can see, average time of last is smaller than first, which means that participants tend to obtain a better understanding with the last mission. This proves that Lumos app is sufficiently easy to use. Moreover, the difference in average time between both is more bigger for more complex missions. I'm going to conclude this talk. We designed and implemented called Lumos, which improves smart home interoperability. We fudged that efforts depending on vendor support or architectural changes face fundamental challenges in deployment. Lumos takes a best effort approach that leverages information embedded in IoT apps. Therefore, we do not require any vendor support and any changes to current IoT architecture. Our in-depth evaluation shows that Lumos has high coverage in terms of controllability for IoT devices and platforms, and we requires reasonable effort compared to popular IoT platforms. Thank you for your attention, and I will be happy to answer any questions.
Okay, so anyone have questions? You can raise your hand, or you can simply. Okay, hi, Xiaoming. Xiaoming,
I want to ask one question.
yeah,
So
can you turn on your camera as well? Yeah, sure, we can hear you. Okay, great.
Yeah. So I think the proposal of using the semantic information for interoperability between among different IoT devices is very interesting. I like it. The question is how much complexity would be on, let's say, extracting such information, and what kind of scale when, let's say, how much data you will need to educate those let's say, information extraction phase, so that you can have a more or less accurate or reasonable matching about the between the different device control messages. The cost. Yeah.
Yeah. Okay. Good question. We depend on to extract semantics from only users. We just extract a little semantic information from Android binary, but it is, as I mentioned earlier, it is insufficient always. So user have to our system add semantic tag. Users because it is too easy for human. If a user see this button is it easily infer the meaning of the button, and the button semantics and repair with network messages to monitoring network messages.
May I interpret in such a way that you need to have a certain specification on how you can, let's say, label, how you can, for the normal user to put such semantic summary or keywords into their specification about the IoT device? Or it's using automated machine to extract that?
Oh, yeah, pardon me?
Yeah. So how you can acquire those information? So it's basically the information exchange process I want you to know, and also the scale of such information, how much information you eventually need. And if you have more IoT devices, would this become a major bottleneck? Where is the bottleneck?
Our input are just two. First is Android binary.
Mm-hmm.
We automatically extract network messages and UI information from the Android application automatically. And second input is human. Our system show the information from APK, and user give a hint in terms of semantics.
How much scale is it? So let's say it's tens of small information piece or objects or something, or in terms of I want you to know the cost of doing this learning, right? So you need to match between the extracted information to the real semantic that you want to control the other devices.
Actually, our static analysis module is typically exactly because typically IoT mobile apps are simple in terms of network messaging types. So our mobile app, our Lumos app notified that this time is learning time to Lumos gateway. So at that time, Lumos gateway just focus on some network messages that match network signatures from program analysis page. So we can easily Lumos gateway easily learned the network message.
Okay, we probably I would rephrase this in the Wuhan. Okay, thank you.
Oh, hello, hello. I experienced a disconnection. Okay, so I didn't know what happened in the previous few seconds. Okay, so sorry, I had a disconnection. So does anyone have any other questions? Look, can you hear me? I cannot hear anybody.
Yes. Yeah, we can hear you very well.
Great. I was okay, so did anyone else have a question regarding the Lumos? The very interesting, yeah, controllability and interoperability. Anyway, okay, I have a question. Well, according to my understanding, in order for such controllability to happen, do you need the two IoT devices or several IoT devices to be physically close to each other?
Yeah.
Like what is?
Yeah, pardon me.
Oh, okay, I can say that again. So in order for controllability to happen between different IoT devices, do you need these IoT devices to be physically close to each other? Like, do you need them to be close to each other?
Yeah. In our data set, there are many IoT devices are in one network. And yeah.
Okay. Did you evaluate kind of the impact? Yeah, the distance between the devices, do you need them to be near each other or they can be far away from each other?
When I started this research, we assumed that people want to control IoT devices in physically nearby network, and but Lumos app. But if an interoperation rule is registered on Lumos gateway, the rule is automatically operated. The location is not matter. Automatically operation the rule. Yeah.
I see. Okay, I see. So does anyone else have any questions? You can raise your hand or turn on your speaker automatically. Do you have a question? Okay, maybe we'll move on to the last speaker. So thank you, Jeongmin. Thank you for the nice presentation. Okay, so great. We have the last speaker, Yu Sun, and Yu Sun received bachelor and master degrees from Dalian University of Technology, China in 2018 and 2020, respectively. He is studying for a PhD degree in the School of Software, Dalian University of Technology, and his research interests cover wireless power transfer and wireless rechargeable sensor networks. And today, he will give the presentation of trading off charging and sensing for stochastic events monitoring in WRSNs. So, Yusun, you can start your presentation.
Okay, hello. Can you hear me?
Yeah, you can switch on your camera.
Okay, can you hear me?
We can see you.
Is it okay?
Yes, we can see your PowerPoint as well. Okay. You can start. You can start.
Okay. Thanks for the session chair for the introduction. And it is my pleasure to attend this meeting. The title of my presentation is Trading off Charging and Sensing for Stochastic Events Monitoring in WRSNs. And I will introduce our work from these 5 aspects. background model, solution, theoretical analysis, and experiments. Firstly, let me briefly introduce the background of this work. The traditional Internet of Things suffers from the energy bottleneck, and the technology of wireless power transfer realizes the remote and reliable supply for large amounts of energy, and provides a new solution to solve the energy bottleneck problem of wireless sensor networks. On this basis, the wireless rechargeable sensor network is generated. We call it WRSN for short. And WRSN is a new type of wireless sensor network with wireless power transfer technology. In WRSNs, rechargeable sensors are equipped with supercapacitors and can be charged wirelessly. A wireless charging vehicle travels within the network and provides energy supply for surrounding sensors. But at present, the research of WRSN is mainly based on simulation environments. And however, in the actual scene experiments, we found the phenomena that when the sensors cannot work when being charged, and we call this phenomenon charging exclusivity. It is because that the charging and discharge states of supercapacitors cannot coexist, and the sensor node always have simple structure and have no power control circuits. And as a result, the charging and sensing cannot be conducted at the same time. So when a sensor is being charged, its sensing task is suspended until the charging process is finished. And so some important events during the charging process may be missed. As a result, some serious consequence may be caused. And as we can see, there is a serious conflict between experimental phenomena and simulation assumptions. So simulations often ignore the charging exclusivity issue, and so existing charging schedulings may be unreasonable, so possibly causing serious consequence. So this motivates us to propose a scheme which is not only suitable for simulation performance, but also has excellent performance in practical applications. So when solving this problem, we face with several challenges can be concluded as the first. It is non-trivial to quantitatively leverage the utility gain and utility loss yielded by the charging behavior of WCV, the charging vehicle. And secondly, the solution space of solving this problem is infinite. And thirdly, constructing the traveling path of WCV is equivalent to solving a traveling salesman problem. And finally, the objective function of this problem is nonlinear and hard to analyze its properties. So after solving these problems, our contribution can be described as follows. First, to the best knowledge of the authors, this is the first time the charging exclusivity issue is investigated. And in this paper, we formalized the CEO problem, named CEO, to maximize the charging utility. And secondly, we present a new area discretization method, which can effectively solve the problem of infinite solution space and plays a good role in path planning. Thirdly, we propose a practical application-oriented stochastic events monitoring model for WRSNs, and prove that the good properties are held for the objective utility function. And at last, an approximation algorithm is proposed to solve the problem effectively, and we prove that our proposed algorithm has a bounded approximation ratio. So next, I will introduce the model of our network. In our network model, there are three network elements. There are sensors, points of interest, and certain spots for WCV. In the network, the sensors monitor stochastic events at all POIs within a sensing range, and the stochastic events are generated following a certain pattern at POIs. For the WCV, it travels within the network and stops at certain spots to charge surrounding sensors. For the event model, we claim that at a POI, stochastic events are generated one by one in a certain pattern, and event occurs independently with each other in both temporal and spatial dimensions. And what's more, the duration of events and the interval between events are random variables too. And so under this assumption, the event generation process at a single POI follows a Poisson process. And the monitoring probability of a sensor. So the sensors monitor surrounding POIs with a corresponding success probability. This probability from a sensor to a POI is calculated as follows. And due to the charging exclusivity issue, the probability is 0 when the sensor is being charged. And if a POI is monitored by several sensors simultaneously, we can also calculate the total monitoring probability. And for the monitoring utility, I will introduce the computation of this utility. And when stochastic events are monitored by sensors, the monitoring utility is generated. We give the monitoring utility generated within unit time. And for the monitoring utility is calculated as the integral of unit utility within the event duration. And since the duration of an event is a random variable and the time of occurrence is also random, we can calculate the monitoring utility through the following equations. And by considering all the possible events within POI's lifetime, we can obtain the total monitoring utility. So before and after charging, there are two utilities. We calculate them separately, and their difference represents the influence of charging scheduling. And the charging model are given below. The power transmission model is shown in the equation, and the energy consumption of WCV is divided into two parts. The first part is charging cost. It is generated when the WCV is charging sensors, and the second part, traveling cost, is generated when the WCV is traveling on its path. So after introducing the model, we can formalize the charging exclusivity optimization problem. We call it CEO problem for short. And the CEO problem is described as how to select the appropriate surgeon spot set X for WCV to charge surrounding sensors, such that the total charging utility of the network and their charging exclusivity is maximized. We note that the CEO problem has infinite solution space, non-intuitive nature, and it introduces an NP-hard traveling salesman problem. So the CEO problem is the coupling of multiple challenging problems that has high computational complexity. And next, I will introduce our proposed solution. First, in order to reduce the infinite solution space into a finite set, the continuous network area is divided into several sub-areas through area discretization. Firstly, we use a piecewise constant function to approximately represent the charging power. And then we draw concentric circles centered at each sensor and form several sub-areas. And within each sub-area, the charging power at any spot is considered as uniform. However, the curved polygon sub-areas formed by the circular discretization brings difficulties to the following path planning problems. So we propose polygonal discretization to modify them from the curved polygons to the polygons. So we replace each concentric circle with an inscribed regular polygon inside it. By doing this, we can describe the discrete charging power as follows. With the aforementioned parameter settings, we can, the approximation error of area discretization is bounded, but the sub areas obtained are not all convex areas. So we do a further modification to convert them from non-convex areas to convex areas. Specifically, one of the two forming edges of an inner angle that is greater than 108 degrees is extended until it contacts another another edge. So by doing so, the network area is divided into several convex polygon areas, and we denote the areas as set Z. After area discretization, we can reformulate the CO problem into a COR problem. And the solution space is reduced from infinite to finite. But the transformed COR problem is a nonlinear combinatorial optimization problem, which is still difficult to solve. So as for the traveling path construction, the original traveling path construction problem in CO problem is a traveling salesman problem among spots. And in the transformed COR problem, the traveling path construction is touring among sub-areas instead of spots. So it increases the difficulty. So in circular discretization, the generated sub-areas are curved polygon areas, and touring among curved polygon areas is difficult. So we perform the polygonal discretization, and the generated sub-areas, some of the sub-areas are non-convex, but touring among non-convex sub-areas is NP hard. So we make a further modification and transform all the areas into convex polygons. So we can use an effective algorithm to obtain the traveling path of WCV. And then to solve the COR problem, we propose an efficient approximation algorithm. Firstly, we consider the sub-area selection and path construction at the same time, since different area selection may lead to different traveling paths, and the different traveling paths may influence the area selection too. So the cost-benefit ratio is utilized to evaluate different surgery areas. The cost-benefit ratio is defined as the ratio of marginal benefit growth and the marginal cost growth. And we iteratively select sub-areas according to the greedy strategy. And when cost-benefit ratio is negative, the selection is terminated, since negative cost-benefit ratio indicates no marginal benefit growth is generated. Then we select the sub-areas until the energy budget is exceeded. For each newly added sub-area, we recalculate the corresponding charging utility and the corresponding traveling path for WCV. And if the optimal area we select that exceeds the budget, then we select the suboptimal solution instead. And when any selection will exceed the budget, we jump out of the iteration and compare the output set with the baseline value. The output set is compared to the set with a single element which has the maximum marginal benefit growth, and the one with larger utility is output as the result set. And next, I will introduce the theoretical analysis. Through converting the CO problem to budgeted maximum coverage problem, we simplify the CO problem by ignoring the path planning subproblem of it. And the simplified problem can be described as selecting elements with maximum benefit under budget constraints. And this problem can be reduced to the budgeted maximum coverage problem, which is NP hard. And the part that we ignored, the path planning, is also NP hard, since it is a traveling salesman problem. So the CO problem is a combination of several different NP hard problems. It is also NP hard. So to solve the CO problem, general algorithms cannot obtain the optimal solution in acceptable time. So it is necessary to reduce the difficulty of solving the problem through problem transformation and approximation algorithm. So to ensure that our proposed approximation algorithm has a reliable approximation ratio, these three following conditions should be satisfied. That is, the objective function UX of COR problem should be non-negative, monotone, and submodular. and the definitions are given below. For the non-negativity, we only need to prove that UX is monotone, then we can prove its non-negativity. And for the monotonicity, we utilize the transitivity of monotonicity and submodularity to convert the original objective function UX to a simplified version. And it is given below. And by analyzing the benefits and accidental utility loss of charging behavior, we found that although charging behavior can lead to accidental utility loss, it always makes the objective function monotonically increase. So we proved the UX is monotone. And for the submodularity, we gave the 4 possible relationships among charged, to be charged, and uncharged sensor sets into different situations A and B. And the marginal benefit growth of newly added elements in these 4 cases are analyzed. And afterwards, we analyze the specific charging process and the various relationships. And the charging utility increment under the conditions A and B is quantitatively compared, and the submodularity is proved. We claim that with a slightly relaxed budget, the output of our proposed scheme is bounded to a given approximation ratio, and it is better than the optimal solution with a smaller charging radius. So I will introduce our experiments, and we do both simulation and the realistic experiments. For the simulation, we set sensors to stop working when being charged, and this is because we try to implement the charging exclusivity issue, and several baseline algorithms are provided for comparison, and the simulation parameters are listed on the right. As shown in the figures, by changing various network parameter settings, the corresponding charging utility of different algorithms is compared. And for example, we compare the charging utility of these 5 algorithms in different error thresholds, in different energy budgets, different edge number of polygons, and different event arrival rates. The numerical results indicates that under different parameter settings, the performance of our scheme is 21.3% higher than other baseline algorithms on average. And we also carry out experiments in realistic scenarios. The charging equipment in realistic scenarios is shown in the left figure, and we utilize this equipment to carry out real experiments. We set 10 POIs in an open area and deploy 25 sensors around them to monitor extreme temperature events. We take the local temperature statistical data as the benchmark, and we compare the experimental results with the simulation results and the theoretical results. We can see that there is a gap of 3 to 15% between the theoretical value, experimental value, and simulation value. And we can see that our simulation and experimental results fit well with the theoretical analysis. And we also compare our scheme with other baseline algorithms. For example, on the right, we change the energy budget to different values, and our proposed algorithm always outperforms other baseline algorithms. So through realistic experiments, numerical results demonstrate the feasibility and the superiority of our proposed scheme. And that's all for my presentation. Is there any questions?
Hello, so is there any questions? I think this is a great chance to communicate with the author of the paper. So does anyone, okay, great.
One question, may I ask?
Okay, please.
So you say during charging, you cannot do the communication, but I suppose this is I mean, the sensor production perspective, there's a chance always, let's say, beginning phase, maybe it's exclusively not possible to be done, but with the technology changes, tomorrow this will be done quickly. Just like the beginning of smartphones, you have to use a separate charger to do your battery charging. But now is embedded, you can do whatever transmission during the occur during the charging at all. So I just wonder your work effort here, would that make sense with the technology in the development in the near future, whether this problem still holds that I don't know the industry production, how this is going to happen, but I just want to know your point, right?
Okay, thank you for your question. And we have do some realistic experiments, and we found that the sensors cannot conduct sensing tasks when being charged. And we have researched for this reason, and we found that this is a common phenomenon in the most COTS sensors, rechargeable sensors. And the sensors that we mainly use is produced mainly by the company of PowerCast or WISP or other, but they also in order to reduce the energy consumption, they always have a simple circuit structures. So the supercapacitor is directly connected to the circuit, and there is no power control circuits. And you say that maybe with the development of technology, this issue may be solved, but I think that there will be a long time to solve this question, and this issue is I think it's the bottleneck of the rechargeable sensors. So it should be solved now. So I think this is the meaning of my work. Yeah.
Okay,
thank you.
Thanks.
Hi, so does anyone else have a question for you? Yes, so just take this opportunity to interact, to ask any questions, and to communicate with the author. Okay, so if there is no question, I have a question. So my question is, you consider this kind of exclusive. Anyway, so the trading between charging and sensing. My question is, during the charging, this wireless charging, do you need to charge it to the full, or you can choose like if I am afraid to miss an important event, can I choose to charge it like halfway, not 100%? Is that a choice? And does it?
Okay.
Yeah.
Okay. That's a very good question. Yes.
Okay.
If I charge, in my assumptions, I will the WCV will charge the sensor to the full capacity, and there are some other works that they do not charge the sensor to the full capacity, but this will increase the traveling path consumption, because you should go to this sensor but not charge it to full capacity and go to another sensor, but later you should return back to this sensor to further charge it. So this may be increase our energy budget. And if you charge it for example, for 15%, and later you charge it for another 15%, the time of the sensor cannot, the time that the sensor cannot work is equivalent. So, but I cannot know when some important events may occur. So I have to charge it to the full capacity for reducing my traveling consumption. Yes.
Okay. Does anyone else have any questions regarding this wireless recharging sensing network? Anybody? You can simply like switch on your microphone or your camera to just shoot out the question. Okay, if there's nothing, I have another question. So
Okay.
you assume like I guess for most of the cases you assume that the happening of the events of the important events are follow the Poisson distribution, but sometimes it may not be the case. Like in internet traffic, the internet traffic, they are bursting instead of following a certain Poisson distribution. So does that assumption affect much of your solutions, or did you test maybe other distributions of the important events? How does that influence your solution?
Yes, this factor, the pattern of the occurrence of stochastic events will do not influence the performance of our scheme very well. So if I change another event occurrence, our scheme can still perform well. So I just take the Poisson process as an example. For any other patterns of the stochastic events, our scheme still works.
Okay.
Its performance does not rely on this distribution. Yeah. Thank you.
Okay. Nice. So anyone else, any of the audience, have any questions regarding the three speakers? It doesn't matter if you do not turn on your camera, you can simply turn on your microphone, and that's okay. So does anyone else have any questions? Okay, I guess not. Okay, so we will welcome thank our three speakers for their excellent presentations. And I think that should you have any further questions, you may reach out to them to further kind of exchange your ideas. I think all the three presentations all gave us something to think, some novel contributions. Okay, that's great. I think we enter into the break session, or we have some time left. And should you have any questions, should you have anything to say, you can speak up. Right, Leonardo? Hello, so you're the host, so...
Yeah, I'm here. If someone has to say something, you can go. Otherwise,
yes.
We will stop here.
Okay, we will just wait till like 6 o'clock. And if you have anything to say, you can come up and say. And so regarding any of the presentation, Okay, so since this is a free communication, so I actually have a question for you, Jeongmin, right? Hi, Kim, Jeongmin, the second speaker. Are you still there? Hello? I suppose not.
At lunch or dinner.
Sorry? Hi.
I think he is probably at dinner, but I'm very interested in the second paper. Therefore, I asked for the paper and now reading it. Yeah.
Oh, that's great. That's great. That's great. Yes. Now, I just want to know if there is any like kind of security problems involved, or how this controllability goes, because I want to dig into the paper as well. Yeah. So it's not it should be camera ready, but it's not, the preprint is not available online, is it?
No, Xiaoming, Yanjiao, it's all on the conference website, so you can go and get it from the ICNP 2020 website. All the PDFs of the papers are there.
Yeah.
Okay. Yeah, great. So we may have a chance to read the paper and to know the details of the paper. Okay, that's very interesting. Okay. Maybe let's see. Let's see. So the first speaker has already left. I think so.
Yes, he left because I cannot see his name.
Okay,
sometimes if we have enough time, we can have the 3 speakers to serve as a panel to discuss the open issues in this area, probably.
Okay, so since the first and the second speaker are no longer here, so maybe Yusuf, what's the future directions in your area in this rechargeable wireless rechargeable sensor network? What are the open questions?
Oh, hello, can you hear me?
Yeah, we can.
You are interested in my future work, right?
Yes.
Yeah. We are working on the robustness of the wireless rechargeable sensor networks. And we have done some work. For example, when the sensors are conducting sensing tasks, some failure may occur, and how to deal with this issue is an important problem to increase the performance of the network. And this is what we are working on. Yeah.
But this does not have something to do with the charging process. Like in wireless sensor, in WRSN, they have such failure problem during sensing.
Yes.
So what's the connection with the recharge part of this?
Okay, maybe I have described the problem not so clearly. When the WCV is charging the sensors, it may have there may occur some failure. For example, the charging power is not stable. Sometimes it will have some disturbance, and if the charging power is not stable, the sensors cannot receive plenty of energy, and it may exhaust its energy. So there may occur some failure. Yeah.
You see, I actually had the same concerns with Xiaoming. Like you say that we cannot work and charge at the same time. Like how far away are we reaching the part where we can have sensing and working at the same time? Like today we can have our smartphone charging and play with it at the same time. So how far are we there? Is it very hard for them to sense and being recharged at the same time?
I think maybe it will take a period of time or several years or tens of years to overcome this difficulty, because the sensors are not like our phones. They have a bigger battery, and the sensors are just equipped with supercapacitors, and the capacity is kind of small, and it cannot go through the heavy tasks. Yes, so maybe after several years, this may be achieved. Yeah.
I see. Yeah. So yeah, naturally we will think that it's better for them to kind of being charged and work at the same time. And I have another question actually. So final question, maybe we are reaching the time. So should it be charged when it is exhausted, or I can charge it if it still has like 50% of batteries. Yeah.
We should charge the sensors before it exhausts its energy, since when it exhausts its energy, it will no longer stay to how to say. So when it exhausts its energy, it will be a dead sensor, and we cannot recover it anymore. Yeah.
I see. Okay, so I think that's all for this session, and welcome. Thank all the speakers and welcome all the audiences. Have a nice day. So Leonardo, what should we do at the moment?
I just stopped to record and that's it.
Okay.
We have a small pause, 30 minutes, and then we will be back for the other session.
Okay, I see we'll have a small break, a virtual. Okay, so
yeah,
bye-bye.
exactly. Thank you very much.
Thank you all. Okay, thank you all. Bye-bye.
Bye-bye.